Okay. Whew. First lecture of the semester for this class. Let's do it. All right. Fair warning. I will probably be doing this lecture in two parts because I have to teach. I have to be in class in person in about 45 minutes. So let us get started. So what we're going to be talking about today is obviously cosmology, but before we can really get into what cosmology is, we really need to start talking about what is science specifically. And so I will, in this lecture, be addressing that concern. I will be identifying certain hallmarks of science and how science is different from, say, a pseudoscience. And then in the following lecture, I will start talking about um, cosmological thought, or at least the beginnings of where the idea of the cosmos came from. So the process of science. Now, you may have heard of this theoretical physicist, although he was a real person, Albert Einstein. You may have heard of him. He said, all knowledge of reality starts from experience and ends in it. Propositions arrived at by purely logical means are completely empty as regards reality. Because Galileo saw this, and particularly because he drummed it into the scientific world, he is the father of modern physics, indeed of modern science altogether. What Einstein is really saying here is he's talking about what we refer to in astronomical circles as the Copernican revolution, the transition from a geocentric universe to a heliocentric universe. And Galileo was the astronomer who really put the nails in the coffin uh, behind that really philosophy or astronomical model. Yes, Copernicus was the first to put together a mathematical model that actually was fairly predictive with the sun at the center. Kepler was the one who actually derived empirically the laws, and Newton was the one who ultimately came up with the laws of gravitation, which explained said planetary motions. But it was Galileo who refuted the driving principle behind the geocentric idea, which was Aristotle. I know people like to tie the geocentric theory to the church, but that's mainly because the church co-opted the Aristotelian worldview. And the Aristotelian worldview was an inductive or is a deductive science. Basically, it's a top-down perspective, or I should say, deductive reasoning. It's a top-down reasoning. You basically assume a conclusion and then come to certain points based on those observed conditions. Whereas Galileo was involved in inductive reasoning, in that he took small experiments, and he took a series of small experiments, took those results, and then built up a framework to explain a larger set of phenomena. It is a bottom-up perspective as opposed to a top-down. Not to say that deductive reasoning isn't a valid form of logic, but in terms of science, we have to approach this. We have to approach science from an inductive standpoint. We have to approach science from a position of ignorance, derive knowledge where we can, and then be able to summarize what that knowledge is into a larger framework, if at all possible. And it was Galileo who first put this together. So how do we distinguish a science from non-science? The first thing we naturally would want to do is we would want to define science, the word science. But unfortunately, that really isn't all that helpful. Science is derived from the Latin scientia, which simply means knowledge. However, it should go without saying that not all knowledge comes from science. You can have artistic knowledge, you can have poetic knowledge, you can have emotional knowledge. You can have knowledge in a variety of different areas that have nothing to do with science. So just knowledge is a very poor definition to encompass any and all things that are science. It's far too broad and far too subjective. So the first thing we need to do is we need to find a certain definition of terms. We need to find a set of terms which we can all agree on. Therefore, when I say the word fact or say the word theory, you know what I'm meaning in terms of scientific inquiry. I always tend to do this in arguments or in discussions. Is when I have a discussion with somebody, I always like to define certain terms so there's no misunderstanding as to what we're actually talking about. From a scientific standpoint, a fact is an observation or measurement that can be confirmed by someone else or something else. The fact that I'm 6'2", or actually now 6'1", yay shrinkage. Getting older is so wonderful. That I am 6'1" is a fact because it doesn't matter if I measure it, it doesn't matter if you measure it, it doesn't matter if an alien came down from Alpha Centauri, they would measure that I was 6'1", assuming they knew what the hell a foot was. That is an empirical fact. A hypothesis. An hypothesis is an idea which leads to, and this is the key bit, a testable prediction. A hypothesis is a statement where that statement can then be falsified if at all possible. If an idea cannot be tested, then that's all it is simply just an idea. It's a nice little mathematical model, as it were. But until it can be tested, it is not truly a hypothesis. And that is really what drives science forward, is this idea of testability, is this idea of putting forth ideas and then determining whether or not they are true, or rather whether or not you can find evidence to support that they are true. A law. A law is an expression, typically mathematical in form, that describes a certain natural phenomenon. There are many such laws. There is a law of gravitation, there is Boyle's law, there is Hooke's law. These are all laws which describe very specific actions or forces that are happening within the universe. And they are, as I said, mathematical in nature, because mathematics and science are invariably tied together. You cannot really have one without the other. Mathematics is, I think of mathematics as a language. It is the fundamental language of the universe. It is really how one fully describes how the universe came into being. And it is, in certain cases, just amazingly elegant. As I always like to say, some of the most powerful equations are some of the simplest. F equals ma, E equals mc squared, E equals hf. I mean, these are powerful statements that energy is equivalent to mass, is such a fundamental part of our universe that it can be so fundamentally simple is mind-boggling to me. So mathematics is an essential part of the scientific method. What about theory? Now, theory is the term that is most often misconstrued or misused. Now, to put on a certain cap, according to dictionary.com, that lovely source, the first definition of dictionary.com says it is a coherent group of tested general propositions commonly regarded as correct that can be used as principles of explanation and prediction for a class of phenomena. So this is what we scientists would refer to as a theory. Excuse me. Scam phone call. Anyway, this is what we refer to as a theory, scientifically speaking. A scientific theory is a group of ideas that have been rigorously tested over time and not falsified, or have not been falsified. All of the evidence collected during those tests have been in support of this framework of ideas, which we refer to as a theory. Examples of this are the theory of relativity. A theory, scientifically speaking, does not does not, how should I put this, does not invoke uncertainty to a certain extent. It is true that nothing is proven in science. Everything is provisional. So if someone tries to tell you that they've proven something, either they're lying or they're trying to sell you something. No scientist worth their salt is going to tell you that anything in the universe is proved. All they can really say, if they want to be honest, is that the evidence that we have at the current time suggests this is true. But you must always keep the door open for being wrong, or more likely, being incomplete. Newton wasn't exactly wrong. Classical mechanics is just simply incomplete. It works beautifully for large things moving very slowly in the absence of large gravitational fields. But if any of those conditions are violated, then Newton's laws, classical mechanics, fails, and we have to use relativity in order to properly explain the motions of objects. This is in opposition to the more colloquial term of theory, or the way theory is defined. And that is by number 6 of dictionary.com, which is a contemplation or speculation. As in, I have a theory that Jeffrey Epstein was killed by the Clintons. It's not something that I suppose it can be proven, but it's really just it's a conjecture based on subjective data. It's really an idea, and typically, colloquially in theory, we often will confuse theory colloquially with hypothesis scientifically. In that someone says, I have a theory that Jewish space lasers are starting California wildfires. Well, great, that's an idea. If you can go ahead and show that there's evidence for that, good on you. Well, there ain't, but if you can find some, I'm willing to listen. Because as scientists, we must always be willing to listen. We must always be willing to keep an open mind to new ideas and new suggestions, no matter how outlandish, assuming they have evidence to back up their claims. Hallmark number 1. Science is an exploration. Now, most scientific, although that's in itself a subjective term, but I would say that when people think of
Rob is wrong, Rob is right.
That's true. When people think of a scientific theory, or excuse me, when people think of scientific work, sorry, I've got to keep that on because I've got a timer running. But anyway, when people think of a scientific work, what they think about is, people in lab coats doing controlled experiments in a laboratory, being able to control all the variables and, only being able to think about, the independent variable versus all the dependent constants and all that kind of good stuff. And that is how physics works typically, is that they are blessed in the sense that they have the ability to capture whatever whatever it is they want to study within the laboratory environment. However, that's not how all science is done. Astronomy, for example, is mainly an observational science. Only a small fraction of astronomy is done or can be done in the lab, because astronomy deals with the largest and smallest things in the universe. There is no way that we're going to stick Jupiter in a lab and figure out how much it weighs simply by putting it on a scale. There's no way to go to the sun and go into the interior of the sun to find out to observe exactly what is making it tick. We have to use indirect methods. We have to observe indirect methods, or I should say, we have to use indirect methods of observation to determine or to measure the facts of the universe in order to create our hypotheses and then thus create our theories. The social sciences, those are also sciences. And they use survey work in order to determine basically test their hypotheses. Survey work, a lot of people knock survey work, but I can assure you that I have colleagues who have done it, and there is stringent guidelines as to what makes a good survey and what doesn't. In the same way that there are guidelines to explain what makes a good laboratory experiment and what doesn't. So, an example of a experiment or an observation that tests a physical theory in astronomy, Einstein predicted that massive objects will cause space to bend. And because space bends, light itself will also travel along that bent path. Meaning that lights in the sky, stars in the sky, will shift in their position based on whether or not there is a massive thing in the way, like, for example, the sun. And so Eddington tested this idea of the theory, and this was the first rigorous test of Einstein's theory of relativity. Eddington knew that there was going to be a eclipse on an island off the coast of West Africa in 1921, I believe. He knew that there was going to be an eclipse on a particular day. So what he did was 6 months prior to the event, he went to that same island, to the same location that he was going to observe the eclipse, and he measured what well, maybe not 6 months in advance. Scratch that. Probably, 6 months. Sorry, 6 months in advance. He measured the night sky that the stars that the sun was going to pass through. He measured the distances between those stars very accurately, or at least as accurately as he could at the time. And then he came back during the eclipse, and when the eclipse happened, the total eclipse blocked out the sun for a few minutes, and the sky got dark enough in order to see those stars again. And then he measured those stars once more. He took a photograph and he measured what those stars looked like, or what the distances of those stars were, and he found out that yes, they were discrepant. The distances between the stars during the eclipse was larger than the distances where the sun was not present. The only explanation is that the sun caused the light to bend, making the stars appear as if they were more spread out than they actually were. Homework 2. Science deals with physical phenomena, that which we refer to as reality, not metaphysics, not things in the realm of the spiritual. Science deals with hard and fast evidence, things that we can tangibly show to be true, measurements that we can show to be true. A scientific model does not include, say, for example, divine intervention. We have moved past the idea of lightning being caused by Zeus throwing a fit and throwing his thunderbolts around. Personally, I am a man of faith, and so I am not trying to disparage religion in any way. But to me, religion and science don't need to be at odds. They don't need to be at loggerheads with each other. They describe reality, or at least they describe the universe, but in two completely different and completely separate ways. My ability to do science is not affected by my religious viewpoints. My religious viewpoints are not affected by the conclusions I come to through my scientific endeavors. They are two separate ways of inquiry to learn about the universe itself. One should not affect the other in either case. Homework 3, whereas Occam's razor. If two hypotheses explain all observations equally well, then we should use the one that requires the fewest assumptions. This was first stated by, I think his name was William of Occam. He may have been a monk. I'm not entirely certain. I still don't know what razor means in this context. Eventually I'll figure it out. But Occam's razor, or as my father would like to put it, Keep it simple, stupid, or KISS. What this basically means is that if you have two models that explain a set of observations equally well, whereas one is no more predictive than the other, then you must default to the simpler of the two models. This may seem like a fairly innocuous idea, but it was the driving force behind the Copernican revolution. Nicholas Copernicus's model, which had the sun at the center, was not perfect. And actually, because it still used circular motion, it wasn't any more predictive than the Ptolemaic system before it. But it wasn't any worse. And it was far simpler to use. And so that is what drove Kepler, for example, to look at his idea, to look at Copernicus's model and say, maybe he's onto something. Maybe the idea of putting the sun at the center of the universe, or the known universe at the time, actually has some merit. Maybe maybe this is the right direction to go. And so that was what led Kepler down the road to define his three laws of planetary motion. If the model is simpler, it is more likely to be true, particularly in the case if they can explain two of the same phenomenon equally well with a competing, more complicated model. Hallmark 4. You must be able to leave it behind, as I like to think of it. If an idea is proved to be wrong, if Einstein's theory of relativity, if there was a test and someone tested the theory of relativity and got results that were verified by other folks that did not jibe with theory of relativity, where Einstein's theory predicts something else would occur, then that theory must be either rejected outright or, more than likely, amended in some way. For example, the solar nebula theory, or the Nice theory, because obviously it came out of Nice, France. The Nice theory was the theory that the solar system came into being from a protostellar cloud, and the star formed at the center, the sun formed at the center, and the planets formed in a disk around it. And that was great. And that theory seemed to explain everything that was in our solar system. And then we found exoplanets. And that kind of threw a monkey wrench into everything. Particularly the first exoplanets that we found were in places where we did not expect them to be at all, which were not able to, the Nice theory at the present time was not able to accommodate. They did not, the Nice theory, for example, could not explain why you would find Jupiter-mass planets at the distances that we were finding them, so close to their host stars. So the idea of planetary migration had to be added to the theory. The theory wasn't rejected wholesale. It was modified in order to allow for these cases of these exoplanets to exist within the framework of that theory. So a scientist must keep an open mind. They must be able to reject if the data points in that direction. If the data rejects a certain paradigm of thought, then we must move forward and keep going. Hallmark 5, and this is where I'll end this section of the lecture. Hallmark 5 is the cosmological principle, which is a evolution, as it were, of the Copernican principle. The Copernican principle states that there is nothing special about our place in the universe. But more generally than that, there is no special place in the universe at all. No one spot is more special than any other spot. They are all equally special. So it is just as valid to say that I'm the center of the universe than you are the center of the universe. Both of which have as much meaning as they have, because there is no preferential spot in the universe. So the universe is what we call isotropic and homogeneous. It looks the same in every direction and is the same in every location to a large enough scale. And we'll explore those concepts more later on. The other thing about the cosmological principle, and this is vital in terms of astronomical understanding, particularly in terms of cosmology, is that we have to assert that the physical laws which apply to us here on Earth apply everywhere in the universe at all times. Meaning that if I drop Mentos into a Diet Coke bottle, it's going to explode. If I go to Io, drop Mentos into a Diet Coke bottle, it's going to explode. Io is one of the moons of Jupiter. If I go to the Andromeda Galaxy, again, explosion. If I go to the farthest edges of our visible universe, again, explosion. If I were to do this experiment now, explosion. If I were to do this experiment 5 years from now, you got it, explosion. So physical laws are the same at all times, at all locations. All right. Next time when I revisit this, I will talk about the scientific method. Okay, and we're back. All right, so as you can see from my change of clothes, this is the next day. So where did we live off? Last time in this lecture, so maybe 2-3 minutes ago for you, a day for me, we were talking about what is science, what separates science from pseudoscience. Now we're going to talk a little bit more about the process by which science is done, and that is commonly known as the scientific method. Now the method that I'm showing you now is a very rudimentary, bare bones approach to how science is done. It is essentially the philosophical framework, as it were, for how science is done. It is by no means a hard and fast system, and in many cases, depending on the field of study, this method can be altered in specifics. And specifically, what I'm thinking about is the difference between a laboratory science and an observational science like astronomy. But to begin with, you need to have a question in mind. You have to look at facts, some observed facts, and question why it is that you see those particular facts, or why is it that those observations seem to follow each other. Then you go into the research, you go into the literature, and you find out everything you can about that type of phenomenon. So for example, if I wanted to know why there are spots, star spots, on a particular star, I would learn everything that I could, not only about how star spots are created, but also about how or why that particular type of star would have spots on its surface. So you do background research to basically to formulate or to better formulate that first question. So that first question is maybe why do star spots occur? Whereas your hypothesis states that star spots occur on this particular type of star due to, say, rotation. And then you'd have to test that hypothesis with a series of observations. And again, I'm going to be couching this in terms of astronomical, couching this in terms of astronomy rather than, say, any other side, because, well, obviously. So you would construct an experiment or a series of observations in order to test this hypothesis, to see whether or not the spots are in fact generated via rotation or not. You would then say, for example, you would look at a sample of stars that are highly rotating, see if there are spots on them. You look at a sample of stars that are not very well rotating and see if there are any spots on that, and see if you can find any sort of correlation between the two. For example, if most or all of the rotating stars have spots, whereas most or all of the non-rotating or slowly rotating stars have no spots, then you can definitively say that, well, you can say that you have strong evidence to support your hypothesis. If that's not the case, then you would have to suggest that you have strong evidence that your hypothesis did not hold true. If it's true, then you would report those results. Now, this is where it varies a little bit. In some cases, you actually want to report what is known as a null result. You actually will want to report the trial or the result of your observation, or the result of your test or set of observations, and to illustrate, no, in fact, my evidence suggests that it has nothing to do with rotation. That is equally important because essentially those types of studies allow the next generation of scientists or scientists within your community who might have that same question, they might say, oh, well, this study has already been done, and the answer is pretty much no. And they might come up with another hypothesis. They might look at your results and say, well, maybe I could refine this method and look at a different type, or look at it in a different way, and basically reconstruct the hypothesis, and then perform their own test to see whether or not it may not be due to rotation, or it may be due to rotation, but a particular type of rotation. So they would construct a different set of observations in order to test that. That's the basic framework. Ask a question, do the basic research, do the background research, construct a detailed hypothesis which has testable implications, test those implications, analyze the results, and determine whether or not those results support your hypothesis or don't support the hypothesis. In both cases, you pretty much want to report your results, but in the case of not supporting your hypothesis, you can easily go, but you or someone else can easily go back, readjust your hypothesis, and test it again to see whether or not maybe there's a little bit more nuance in what is going on. So this is basically just saying the same thing reworded. Is first you start off with an idea or set of facts, you construct a hypothesis which makes a prediction, you test that, and repeat. So this is essentially how or why science is provisional, because scientific knowledge only holds up to whether or not it passes tests, if it passes predictions. If you cannot accurately predict future events, then you really do not know what is physically happening with that object. So up until the point that you test it, you don't really know, or you essentially have a certain basic knowledge of what's going on. And until you provide more tests, you either won't be able to get that knowledge in more detail, or that knowledge, or the knowledge you believed you have, may in fact be wrong, or needs to be highly adjusted depending on those tests. So this is how science goes, roughly speaking. There's a lot more to it, particularly in terms of what regular science does as opposed to paradigm shifting science, but that's the basic idea. Now, I'm going to go through a case study of how this has been going on, how this type of idea can actually span not just decades or years or decades, but centuries. And this is in terms of exoplanets. So it first started off with a question, or more specifically, it started off with speculations as to whether or not exoplanets existed. And Giordano Bruno and Isaac Newton both came to the same conclusion with pretty much the same rationale. Their rationale was that if God's creation is infinite, and we see a solar system with planets going around the sun here, then it only makes sense that this system would be replicated in other places. And so both of them came to the conclusion that exoplanets were just a natural consequence of the creative process of the universe, or the creative, or rather, God's creation. Now, you may have heard that Giordano Bruno was burned at the stake, and some would like you to believe that it's because of this. Actually, he was burned at the stake for 8 reasons. This is one of the lower ones. So he's not quite the martyr to science that folks like to point him out to be. Anyway, these ideas were just that, because there was no way to really test them given the given the tools they had at the time, and really there was no one who came up with any sort of idea of how to test it, even if you did have that equipment, up until around 1952 with a gentleman by the name of Otto Struve. And he suggested that you can use the Doppler effect in order to find exoplanets. By this point, they were using the Doppler effect to find binary stars, 2 stars which are orbiting around the common center of mass. Struve extrapolated this to basically assume that the other star, the other companion, was much lower mass and go down to the planetary mass. The mechanics are still the same. Because you have 2 bodies and they are acting on each other equally through gravitational attraction, as one orbits the other, they're basically actually orbiting each other around a common center of mass, which means not only is the orbiting body moving, but the body that is orbited also moves. So, for example, the sun does not sit at the exact center of the solar system. As the planets revolve around it, it revolves around the exact center of the solar system. And so what this means is if you were to look at the color of the star, as the Doppler effect illustrates, if the star is moving towards you, you should notice that the light becomes slightly bluer. Not perceptibly so to your eye, but through detailed measurements, you should be able to determine that the light is slightly bluer for a time. And then as the star wobbles around and moves away from us, then the light will become slightly redshifted, and that will happen with a certain periodicity equal to the period of the planet which is orbiting around that star. And the degree of shift tells you how fast that star is moving, and that in turn gives you an idea of the mass of the planet going around it. So while you cannot see the planet, you can see the effects the planet has on the star. And that is known as Doppler spectroscopy. But unfortunately, Struve in 1952 did not have the technology in order to test, or in order to see such minute changes in the Doppler effect that would be created by such a low mass planet. A high mass star produces a very large Doppler effect. It basically swings around its companion very readily, whereas a planet, it really barely causes it to wobble. And so in the 50s, they just didn't have the capability of determining that. Now, there are other ways to determine whether or not something is a planet exists, and they're basically the same idea, just different observational techniques. So, for example, it's still the idea that a planetary body is going to cause a gravitational effect on the star. Now, there have been a couple of false starts before we actually get confirmed exoplanets. The first one was made by Jacob and C, where they looked at a binary system called 70 Ophiuchi, and they noticed what they refer to as orbital abnormalities. So if you have 2 stars that are orbiting around a common center of mass, that pretty much operates like clockwork. We can know the period, we know the orbit, and depending on if they're well separated, then that orbit is stable, and they move in a very, very predictable way. We can solve analytically the two-body, that is called the two-body problem, and we can solve that directly. Unfortunately, what they saw was that their predictions of where these stars would be in future times was off. And the only thing, or I shouldn't say the only thing, but their prime suspect as to what was causing these anomalies was the fact that there must be some dark body present. There must be some third body orbiting around in the system that they could not detect visibly. And their hypothesis was that this was a planetary body. Unfortunately, a mathematician by the name of Moulton demonstrated that if you put in any kind of mass, any third body with any kind of mass to it, the system becomes wildly unstable, and essentially the system breaks apart and is no longer bound. Stars fly off in random directions, and the planet would become rogue. So, more than likely, this isn't, unless we are looking at this system at a very, very unique point in time, it is more than likely not the case that these observations were found or were caused by a planet. And unfortunately, this is a cautionary tale, because while Jacob saw this result and accepted it and moved on, C never did, and he became ostracized within the community because he refused to accept what the experiment that Moulton did and then others after him did, which illustrated that no, there was no, in fact, exoplanet to be discovered. And like I said, C went to his grave believing that he was the first to discover an exoplanet. In sort of a similar vein, a very celebrated astronomer by the name of Peter Van de Kamp also believed that he had discovered the first exoplanet by looking at Barnard's star. Barnard's star has the distinction of being the fastest moving star in our galaxy. So when we look at the night sky, we have the illusion that the stars are fixed, that they don't move relative to each other. That's not actually the case. But because the distances are so vast, even the high velocities that these stars move, we're talking hundreds of kilometers per second, because the distances are so vast in space, they appear as if they're fixed on even long time scales. But Barnard's star is the fastest moving across the sky. And what Van de Kamp noticed was that if the star were, in fact, single, if it did not have a companion whatsoever, it should move in a straight line. Newton's first law. If an object in motion will stay in motion unless acted upon by an outside force. Now, if there is an orbiting body, it's going to cause a deflection, and that's what you see in this plot. RA is essentially stellar longitude, declination is essentially stellar latitude, and he believed that he saw deviations in the star's position over time that were periodic. Unfortunately, when he came out with this, again, Van de Kamp was a celebrated astronomer, so it wasn't just some crank off the street. People really was like, wow, all right, so if he found this, then this must be worth investigating. And so everyone started looking at Barnard's star to see whether or not they could confirm his observations. And that's yet another important piece of the scientific method. Your results must be replicatable. When you see observed phenomenon, other people must be able to see that same phenomenon in the same way that you did in order for it to be accepted. But unfortunately for Van de Kamp, no one could. These results at other telescopes were not seen. Barnard's star just appeared to move in a straight line. Now, it's more than likely, now that we've, with some time, because Van de Kamp, again, went to a grave believing that his observations were real, that he had discovered an exoplanet. And so again, because of his reputation, it was investigated as to why he could have been wrong, because his data clearly showed a deviation. And we believe there was actually systematics within the telescope, that given the orientation of the telescope when it was looking at that part of the sky, there was some small amount of vibration that happened with the telescope. And so it wasn't the star that was moving, it was actually the telescope itself moving. That's the leading hypothesis for why Van de Kamp saw that he did what he did. Confirmed detections. Now let's get into the realm of actually finding exoplanets. Now, and what is amazing about this is that the first exoplanet detected, they weren't even looking for it. It was a serendipitous discovery because it was around an object no one expected to have planets. And this is a pulsar. So in 1992, observations of a particular pulsar with the romantic name PSR B1257 plus 12, one of these days I'll have a vanity plate made with that number. They were looking at this pulsar. Now, briefly, what a pulsar is a stellar remnant. It is basically the guts of a dead star that is rotating very, very quickly. We're talking one time every one or thousands of times per second. And this is an object that is about 3 kilometers in size. So think of it as an object the size of the city of Fairfax rotating 1,000 times per second. Now, a pulsar is distinguishable in the fact that it has these radiative jets that shoot out from one side to the other. And if it's oriented properly, when it rotates, that jet will pass by the Earth, and we can detect radiation from that pulsar. And that is an excellent cosmic clock. Because again, Newton's first law, this thing is rotating. Unless there is something else there to prevent it from rotating or to alter that rotation, then that rotation is going to be stable over all time. And so they were looking at, unless, like I said, unless there is some other physical mechanism for why it shouldn't. And that's what the investigators were looking for. Some way for this. They were testing a hypothesis to see whether or not this particular pulsar was slowing down for some reason. But what they noticed was that the time did change, but it changed periodically. It would appear, the rotation appeared to slow, and then speed up, and then slow again in a very measured way. And again, these are very precise measurements. The pulsars make for excellent cosmic clocks. And so the only real explanation that we could come up with, or that people could come up with, is that this pulsar was being affected by a second body. There was a gravitational influence by some other object. And because the timing is so precise, even for the instruments that they were using in 92, they were able to determine that the planet was actually Earth-sized. So you're talking about a planet which is around a dead star that had previously gone through a supernova event. So it's still very much of an open question whether or not that planet was an original planet, meaning that it somehow survived that supernova event, or if it formed from the material of that supernova. Basically, the material shot out from the star during that explosion, condensed back into planets after it was expelled. That's still much of an open question. In 1989, a little bit prior to that, an exoplanet was technically discovered around Gamma Cephei using that Struve method, using Doppler spectroscopy. But unfortunately, the data was so noisy that while the signal was there, it couldn't be confirmed confidently enough. Basically, the evidence wasn't strong enough for them to make the definitive claim, yes, this is an exoplanet. Because other folks looked at Gamma Cephei and they couldn't quite tease out the same signal that David Latham and his team were getting. And so it wasn't until 2002, when observational techniques and observational technology improved, that they looked at Gamma Cephei and actually were able to confirm that, yes, there is in fact a planet going around that particular star. So while it was discovered first, it wasn't confirmed by the scientific community via more observations and better techniques until 2002. Which finally brings us to, if you were to Google the first exoplanet ever discovered, you would inevitably get to 51 Pegasi b, which was discovered and confirmed in 1995. The observations were definitive enough to rule out any other possible mechanism of variability. And so it was the first exoplanet to be discovered around a solar-type star, or a star very much like the sun. But again, it was unexpected. It's what we call a hot Jupiter. Basically, this is a star, or this is a planet, half the mass of Jupiter, half the mass of Jupiter, revolving around its sun in 4 days. To give you an idea, in order for that to work, it has to be 10 times closer to the host star than Mercury is to the sun. Now imagine that, a planet half the size of half the mass of Jupiter. So we're still talking about something that is hundreds of times the mass of the Earth, rotating around a star, or revolving around a star, 10 times closer than Mercury. Our theory of planetary formation had no way to account for that. And so that discovery made us rethink how planets are actually formed around stars, or at least it made us rethink how whether or not planets could actually move within a solar system or a stellar system after they were created, or during their creation. Now, science progresses. It's not static, thankfully. Job security. And for the most part, it progresses slowly in increments. It's, we make a certain discovery, we build upon that discovery, we have what is referred to as a certain paradigm, or basically structure to things. For the longest time, we had classical mechanics to describe the motions of objects. And so all of the science of that time that was done seemed to confirm that, yes, classical mechanics was the way to go. Until cracks started to form. Until there were basically certain situations, very specific situations, that Newtonian or classical mechanics, Newtonian physics, just didn't predict it very well. So, for instance, Mercury. It was known for a very long time that Mercury's orbit precesses. We won't really get into the details of that, but essentially, in order for the orbit to precess, or the orbit itself actually revolves or changes its orientation, something has to, even given all of the masses that we know of in the solar system, they would not produce that effect. So classical mechanics could not explain why that precession occurred. So in 1905 and 1910, I think, might have those dates messed up, Einstein, while working in a patent office, came up with his theory of relativity. First, the special theory of relativity, which simply talked about the speed of light and relative motion, and then the general theory of relativity, where he described the curvature of space-time and the influence of mass as a mechanism for curving space-time, as opposed to a mechanism of creating force at a distance, like Newton, like classical mechanics would classify gravity as. And Einstein's theory was so powerful because not only was it able to predict how Mercury moved, but it made several other predictions which were also borne out to be true. And still, there are even more predictions. Like, for instance, gravity waves have been predicted by Einstein since the beginning, but weren't actually observed until about 2 years ago. So there are still predictions waiting to be confirmed with relativity. But more importantly, what relativity did was not just explain these new phenomena, but it also equally well explained Newtonian classical mechanics. Any theory which replaces a pre-existing theory not only must explain this new phenomenon, but it also must explain all other phenomenon which was previously accepted. And Einstein's theory could do that. And so with this slide, I will just say that nature ultimately decides what is good and what is bad. So when we talk about science, and particularly when we look from an astronomical point of view, really what we're looking for is pattern recognition. We want to see things that are occurring regularly or semi-regularly. We want to be able to see whether or not these things reoccur in space or in time, because that gives us more confidence that this is not just some one-off systematic error of a piece of equipment, that this is something that is predominant within the universe. Even if it's, well, I shouldn't say predominant, that it happens within the universe, even if only very rarely. Like, for example, supernovae. Supernovae only pop off a few times every, depending on where you are, how far you look, a couple times a year, definitely only a few times per century, particularly in our own galaxy. But they occur with enough regularity and with enough pattern to how the explosion goes off that we can identify it as a phenomenon which in the solar system. And I will close out by talking about, speaking of patterns, I will close out by talking about correlation versus causality, because this is often talked about when talking about climate science, for example. Climate scientists will tell you that there is a strong correlation between global temperature and global CO2 concentration within the atmosphere. And because of that, the CO2 concentration is actually the thing contributing to the rise in temperature. Now, first, in order to make this claim, you first have to identify that there is, in fact, a correlation. And so we have, for decades and centuries, we have had fairly precise measurements to be able to determine what the global temperature, or rather the global temperature anomaly, actually is. And so that's what you see plotted on this plot. So they chose a particular temperature and said, this is kind of our 0 point. And then they plotted all the temperatures relative to that. So the blue lines represent temperatures which were cooler than that fiducial point, and then temperatures which are higher. And while you can see there is some variability, or there's some irregularities in the data, particularly for some reason in the 1940s, it was a lot hotter in the globe than not. But overall, when you look between 1880 to the present epoch, you notice a clear rise in global temperature. We also have fairly sophisticated ways of determining what the concentration of CO2 is in the atmosphere over that exact same time, and we see over that black line that, again, it also has increased. Now, this is the key point. In order to determine whether or not correlation and causality is a thing, because climate change deniers will point to something like this, where they will say, well, look at this, the CO2 concentration is steadily rising, whereas the global temperature is fluctuating up, down, and up, down. This is what we call cherry picking. Is basically they are choosing a data set or a subset of the data in order to prove their own point, to show that there is in fact no correlation, so therefore there is no causality. The key point is that there is no physical reason to choose these dates. There's nothing in the 1960s would indicate that CO2 and global temperature were that there was some kind of link between them, nor to the present epoch. But if we go back to here, the reason why we chose the date 1880 is that was the start of the Industrial Revolution. That is when human beings started pumping a lot more CO2 into the atmosphere. Previous to this, it was things worked on primarily wood burning technology. Then when we started being able to burn coal, industry exploded. You had steam engines all over the place. And so you had, we started really dumping a lot of CO2 into our atmosphere. And CO2 is a greenhouse gas. it traps heat. So it makes sense that the more CO2 that's in the atmosphere, the more heat that's going to be trapped within that atmosphere. And so it makes sense that there is a causality between, or there is a link between CO2 and temperature, and also that human beings are the ones primarily responsible for that increase, the increase that we're seeing today. Um, there are some geological reasons why you would expect to see the climate change, either drastically rise in temperature or actually drastically fall in temperature. But we've looked at those causes, we've looked at those phenomena, and we've ruled them out. There is no correlation between, say, volcanic activity and the global temperature. But, and this is one of my favorite things ever, maybe not ever, but I love it. Correlation does not always mean causality, because if there is no physical mechanism which connects the two phenomenon, then there is no causality. For example, sunspots and Republican senators. If you were to plot the number of sunspots, which is the blue line, to the number of Republican senators sitting in office at each particular date, there is a remarkable correlation between those two. And what's really fascinating to me is that black line corresponds to a physical shift within the sun where the polarity actually flips. And even given that, the correlation continues. Now, no one is suggesting that the sun is reacting to the presence of Republicans in the United States Congress. And hopefully no one is suggesting that the Republican senators are perhaps reptilian and somehow affecting the sun as they grow and weight in power within the United States Senate. Hopefully no one is quite that go America arrogant and kind of delusional. So with that, it's a fascinating correlation. There's really no reason for it, so it certainly isn't a causality issue. But with that, I'll leave it. And I know this video is probably going to be fairly long, so I'll just leave it here, and we will talk about essentially the geocentric and heliocentric universes next time.